Hello again. Let's continue on with some more lectures in this logic component of the course. So we're going to start talking about types of statements. So we've seen simple statements and compound statements, but for some of these, we can actually assign sort of names to them because they pop up so often. So we'll talk about these sort of common statement types. This will be a two-part lecture. But let's go ahead and get started. So right off the bat, we're going to start off with a weird word, and that's tautology. So the definition of this is a compound statement that's always true. And so regardless of what the truth values of the original, simple statements are, I don't care about A, B, and C or whether or not they're true or false. The result for this compound statement is always true. And so what that would look like on a truth table is we'd have our A, our B, our C, I mean, maybe even have a D, who knows, or E or an F, maybe you have a lot of them. Let's just say this. Basically what we're getting at is when I have a tautology here, I end up with just true all the way down the line. And it doesn't matter what I put in here, whether these are T's or F's, it doesn't matter at all. If I just have all truths, that's a tautology because it doesn't matter what the original statements are. The final statement, the compound statement, is just true always. So let's go ahead and see an example here. So if I let the statement A be, I'm going for a run, and the statement B be, I wear shoes. This compound statement that I have written here is A and B in an if-then with A. So verbally, we could say, if I'm going for a run and I wear shoes, then I'm going for a run. You might listen to that and you're like, wait, yeah, that makes sense. If you're going for a run and you're wearing shoes, then I'm going for a run. I mean, yeah, I already said I'm going for a run. So that seems kind of obvious, but we could actually figure this out with our truth table methods, and we can actually see whether or not this is always true or not. So let's start off like we're used to with A and B. Oh, something weird is happening. There we go. So I got my A and B, and we're trying to finish off with A and B in an if-then with A. So I better end up, along the way, I better do an A and B. And then at that point, we're actually pretty much there. I can just continue on. So let's go ahead and do this first. Again, we always start off true, 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 false, false, true, false, false. So let's do an A and B. And if we do A and B, we're doing an and. So since both are true, we have a true. And now if there's ever a false, that and ends up being false. So we're looking at our truth tables there. Hopefully we remember them off the top of our heads. So we've got that. Now I just am going to take this A and B, and I'm going to do an if-then with A. And so again, I'm not even looking at this B column anymore. I'm just doing an if-then with this column here and this column here. So I'm just looking across right there. And if I do this, I'm looking at a if true, then true. That yields true. If false, then true. That yields true. If false, then false. And if false, then false. Those are both yielding true. And so what we see here is it doesn't even matter what our original A and B were, whether they were both true, both false, or one of each. I always get true. So this would be what we'd call a tautology. It's always true. And that's just a good example right there. So I can ask you questions. I can say, hey, is this a tautology? And you can tell me whether or not it's a tautology or not by just seeing if it's always true. If there was even a single false in here, somewhere in this line, it's not a tautology then, because a tautology has to always be true. All right, let's move on. So kind of the exact opposite of a tautology, a self-contradiction. So if I make a statement that is always false, then that's what we call a self-contradiction. And that would kind of sound dumb if you said it verbally, because it just doesn't make any sense. It's always false. You're contradicting yourself. So let's look at a similar example. So same two statements, simple statements. A, I'm going for a run. B, I wear shoes. So if I have this compound statement written out in symbol form here, verbally you could say, I'm going for a run and I wore shoes, and I'm not going for a run and I won't wear shoes. And that just doesn't make sense. Again, verbally you can look at this and tell that it doesn't make sense, but a lot of times you can't do that. So let's go ahead and do a truth table for this. So I'll go ahead and copy this guy over. Oh, new page. All right, so we're gonna copy this guy. This is what we're going for in the very end of everything. So we'll start off with our A and our B. For some reason, it's not liking those double lines there. All right, so we've got our A and our B, and let's fill out the standard TT, TF, FT, and FF. And now let's go down the line. We definitely need an A and a B. So let's go ahead and do that. A and B, I'll fill this in rather quickly. We've been doing this for some time now. That and column looks like that. I'm gonna need a not A, as well as a not B, actually. Let's go ahead and do both of those at the same time. I'm trying to change the colors here so it's a little easier to read. Here we go, FFTT, so I'm just negating A, and then FT, FT. And now what we need here is we need a not A and a not B. And that's going to get us almost there. So we'll end up with, we're going to do an and between these two columns. So we're going to have F, 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 T. And now, last but definitely not least, we're going to do an and between that third column and the sixth column. So I'm going to do an and between these guys. Squeeze that in there. And so again, I'm not even looking at the green columns. I'm not even looking at the orange. I'm just looking at this red column and the pink column. And I'm just doing an and between those. And if I do that, I'm going to get false, 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 because I'm looking at an and between the red and the pink. And so that yields all falses. So this is a self-contradiction, right? This is something that full compound statement, it's always false. It doesn't matter whether or not I went for a run or whether or not I wore shoes. This full long, I'm going for a run and I wear shoes, and I'm not going for a run and I won't wear shoes. That's just a completely false statement, no matter what. So there we go with that. That's a good example. Get some practice with our truth tables. Let's move on to the next of our statements, and actually the last of our statements. So we'll talk about logically equivalent. So we've seen so far two different types of statements here in this lecture. We've seen statements that are always true. We've seen statements that are always false. The other interesting thing that can happen is that I could give you two statements that have the same truth values no matter what. And in our definition here, which I'm not going to highlight a whole lot, there actually is an if and only if in here, which can make things even more complicated. But basically, if I give you two compound statements, then you can say that they're logically equivalent, as long as their truth values are always the same no matter what. So here's what I'll do. Let's jump to this example here, and I'm going to kind of cover things up as I want you to not to look at them. Let's not look at any of these middle columns here. So if I start off with the A and B, so let's say I gave you two simple statements, A and B, and you go through your normal, okay, let's start off with our TT, TF, FT, and FF. If you do an if A then B, we did this a long time ago. That gives us TFTT, right? You've got your truth table sheet, and you can look at just if then gives you TFTT. Great, that's all wonderful. So we've got that down. Keep that sort of in the back of your mind. Now let's just go ahead and look at these negations here. We've done this several times already. This is me just negating B and A. And when I negate B, I get that FTFT. When I negate A, I get FFTT. And now I'm going to do an if then between those two columns, between the not B and the not A, right? And that gives me, so ignore this last column out here. Here, let me cover that up. We don't care about that right now. When I do my if then between these guys, that's going to give me that TFTT. And here's what I want to call out to. Again, let's cover all this. I don't want you guys looking at this stuff right now. These two columns here are exactly the same, right? And so what we've determined actually is that these two compound statements mean the same thing. They're logically equivalent. And so we can say that if A then B is logically equivalent to not B, or if not B, then not A. And so again, as I've said, verbally, this means logically equivalent. We use a sort of a triple equal sign to represent that. And so these two statements are logically equivalent because their truth values are the same no matter what. They don't have to all be true or all be false. That's a totally separate thing. That's tautologies and self-contradictions. But if these are the same, then they're logically equivalent. And what we'll end up seeing is there's actually a handful of statements that are logically equivalent. And sometimes it really helps. There have been, in lease agreements and things like that, there are a lot of convoluted phrases and sentences that they use. And if you think about it, why would you ever want to say if not B, then not A? That's just a lot of nots, and you're flipping things in the order around. Just say if A, then B, because they mean the same exact thing. So that's logically equivalent. We've got that good example here. We're going to actually see this example next time. This is what we'll call the contrapositive. I'll call that out right here, just in case anyone's ever heard about it. So that's called the contrapositive, this statement right here. And we'll get into that later. Awesome. Now that we've talked about logically equivalent, I can actually come back to something that we saw back in the days of sets, which probably seemed like a long time ago. When we were doing Venn diagrams and all that stuff, I talked about De Morgan's laws. And De Morgan's laws had to do with unions and intersections. Well, in here, it actually turns out that they work basically the same exact way when you're dealing with truth tables and when you're dealing with compound statements. So these compound statements are logically equivalent to each other. Again, that's that triple equal sign. So if I were to make up truth tables, I would get the same exact truth tables for each of these. That final result would be the same thing. And you can see, just like we saw before in De Morgan's laws, I'm taking this sort of negation before it was a complement when we were dealing with sets, and I'm distributing it in, but then I'm flipping this this or to an and then here I flip the and to an or. So it's sort of saying that you can distribute that negation, but you have to flip the sign of the and or the or, just like we saw with complements and unions and intersection way back when. We're not really going to use De Morgan's laws a whole lot. You're welcome to if you'd like. I'm not going to focus on it too much. I just like pointing it out because it's a great application of logically equivalent statements, and sometimes it can kind of save your butt. So there we go. I'll go ahead and leave it at that, and that's it for this lecture.